My name is Major Merger, also known as Sinclaire Manning. I'm a third-year grad student in the UT Astronomy Department. Thank you for those woos. I like that.
I am Brian Mulligan, also known as Astro a nth-year grad student. Hopefully graduating soon.
Yeah.
Hopefully.
All right. I think I need the pointer for this one.
Okay.
Sorry.
There you go.
First up, for astronomy in the news. So a very exciting detection was made recently of the 21 centimeter neutral hydrogen emission during cosmic dawn. And if that doesn't sound very interesting right away, don't worry. I promise it is. But for a bit of background, the 21 centimeter neutral hydrogen signal occurs from the forbidden spin-flip transition of neutral hydrogen. So the transition is known as forbidden because the timescale of the probability of a single hydrogen atom to undergo it is on the order of millions of years. But luckily, when astronomers try and observe the signal, they're looking at a lot of hydrogen at once, making it more likely to see. So the 21 centimeter emission acts as a probe of reionization, or the time in the universe when the first stars and galaxies emitting high energy photons ionized the neutral hydrogen and began to make the universe transparent as we see it today. So if you look at this top plot, you have a neutral opaque universe, and then the first stars and galaxies start to pop up, ionizing the universe, and then we gradually move into the transparent universe that we have at present time. So astronomers want to know more precisely when this period of reionization started and stopped, and also if we can detect the 21 centimeter neutral hydrogen emission at various stages in the universe's evolution, we can begin to get a 3D picture of the structure of the intergalactic medium during reionization. So taking this 2D picture and turn it into a 3D cube and get an idea of what the universe looked like. So to detect the 21 centimeter signal over large scales, a wideband single antenna radio telescope is used, and it's necessary for it to be wideband since the early 21 centimeter signature occurs over a redshift range of 13 to 27, which corresponds to the frequencies of 50 to 100 megahertz after it's redshifted and stretched to the length in meters. So you have to capture that entire range. So pictured down here on the right, is the experiment to detect the epoch of reionization signature single antenna radio telescope that's located in Western Australia at the Murchison Radio Astronomy Observatory. And then here at the bottom left, and I'm sorry if that's difficult to see for people in the crowd, is the actual signal detected in this lower left-hand plot. So all that for this little dip right here. It's very exciting. What's unexpected about this signal is that the neutral hydrogen appears to be colder than originally expected. And so for this to be the case in general, that means that the neutral hydrogen must have come into contact with something even colder. So what is that colder something? It could possibly be dark matter. So baryon scattering with dark matter particles could drive down the temperature and lead to the larger absorption profile that we see here. But before we jump the gun with dark matter, astronomers must first confirm that this initial signal with follow-up observations. And it's really hard to explain 21 centimeter spin-flip transitions in a single slide, so apologies.
Okay, so as many of you know, renowned physicist Stephen Hawking passed away at age 76 at his home in Cambridge, England, just a few days ago. During graduate school at age 21, he was diagnosed with ALS, or Lou Gehrig's disease, a debilitating neurological disease. Despite difficulty walking, writing, and speaking, and a prognosis of only 2 years to live, he continued with school and completed his PhD, titled Properties of Expanding Universes, in 1966. He is well known for his many public appearances and his book, A Brief History of Time, that explores the origin and evolution of the universe. He has published many books since then, exploring cosmology and black holes, which were his primary interests in astronomy. Within the field of astronomy, he was best known for radiation that is able to escape from black holes that is now known as Hawking radiation. He was an extremely prolific scientist, publishing over 380 refereed articles on black holes and cosmology in his lifetime, the most recent of which was published just this last November. He was an inspiration to millions and will be missed by many of his colleagues and followers.
Nice. All right, so rogue moons. Rogue moons are moons that have been torn from their host planets and flung outward to drift through space, and now astronomers believe they may be as common as stars in the universe. So we know moons are pretty common in our own solar system. Jupiter alone has 67 of them, which makes the Earth's one look a little unimpressive, but you know, we have liquid water, so whatever. But Yu-Chan Hong, an astronomer at Cornell University, wanted to know how moons around distant stars might behave. So previous research has found that many giant exoplanets have eccentric or oval-shaped orbits, and it's been suggested that this could be caused by a gravitational tug-of-war between exoplanets around their stars. So this effect is known as planet-planet scattering, and Hong and her colleagues worked to figure out what this effect may have on the moons of those exoplanets. So she discovered through computer models that the vast majority, around 80 to 90% of the moons around giant exoplanets, are removed by this planet-planet scattering mechanism. And a displaced and destabilized moon then has a few options for what it wants to do. It can go on to collide with a planet or its host star. It can be recaptured through another planet's gravity, or it can go on to orbit another star entirely. But another option, though, is that the moons may go rogue, which sounds very exciting and dangerous. But it really just means that they may fly through space as free-floating bodies, not gravitationally bound to anything. So it is thought that the exomoons in orbits similar to those of Jupiter's 4 largest Galilean moons have the best chance of surviving the planet-planet scattering at about 20 to 40%. And Hong concludes in her recently published paper that these rogue moons may exceed the number of free-floating planets in the universe and could also even be as numerous as the stars.
Okay, next, an exploding star has been caught in the act by an amateur astronomer. Thank you for the amateur astronomers who are here. Victor Busso, an amateur astronomer from Rosario, Argentina, was out with his 16-inch telescope on the night of September 20th, 2016, taking pictures of the spiral galaxy NGC 613, which you can see on the lower left here. He was taking a series of pictures over the course of 1.5 hours just because he thought this galaxy was cool. And the first hour or so just showed the galaxy itself, but the last 25 minutes of his images, he saw a steadily brightening star just below the galaxy. And it's a little bit fuzzy, but right there is the supernova that he discovered. The massive star had actually exploded several hours earlier, but it takes time for the energy of the explosion to go from the center of the star out to the edge. Predicting exactly when a star will explode and when you will be able to see this is pretty much impossible. There's only about one star that explodes per century per galaxy, and there's no way to tell which star it's going to be. The previous closest we've seen to the time that a star explodes occurred in 1987 when a star exploded in one of the nearby galaxies to the Milky Way. It was observed a few hours after it exploded. A few hours after the light first reached Earth. The light during this early phase gives us a lot of information about how these stars are structured prior to their explosion. And it also helps us to understand how gas reacts at extremely high temperatures and pressures that occur within the stars and within this shock wave that's going out as part of the explosion. Most telescopes that are searching for exploding stars like this are dedicated. They're looking across the sky. They're looking for explosions to occur, but they only take a picture of a galaxy perhaps once every couple of days. So the fact that this person, Victor, was looking at this galaxy at exactly the right time is extremely, extremely unusual and lucky. It's estimated there was about a 1 in 10 million chance of him taking these pictures. It's going to greatly advance our understanding of supernova and of large stars. and it's probably going to be quite some time before we manage to capture this again.
You should play the lottery.
You should.
All right, so I know we have at least one Steve in the audience because he's about to give a talk in a few minutes, but just out of curiosity, are there any other Steves in the audience tonight? We got one? Okay, at least one, two? All right, well, this story is all about you, so get ready. So a year ago, a strange new aurora was discovered, again by citizen scientists, so shout out to citizen scientists. Auroras, like Aurora Borealis or the Northern Lights, are produced when charged particles ejected from the sun are drawn to the Earth's north and south poles by the Earth's magnetic field. So once there, these charged particles collide with neutral gas particles in the upper atmosphere and emit the light we observe. So last April, Eric Donovan, a researcher at the University of Calgary in Canada, first heard of Steve while talking to members of a Facebook group called the Alberta Aurora Chasers, who had snapped photos of the phenomenon shown in these two pictures and had given it its name. So, you know, like how folks name their houseplants and stuff. They just called it Steve. So while auroras normally ripple horizontally across the sky, Steve formed a distinctive purplish or greenish vertical streak. Scientists have since coordinated with the Aurora Chasers to combine the dates and times of Steve's appearance with data from the European Space Agency's swarm satellites, which precisely measure a variation in the Earth's magnetic field to work out what conditions cause the phenomenon. And now, almost a year later, on March 14th, scientists led by lead author Elizabeth McDonald, a researcher at NASA's Goddard Space Flight Center, have submitted a paper explaining how they believe Steve forms. So in the region where Steve is observed, there is an electric field that points poleward and a magnetic field that points downward. Combined, these two create a strong drift to the west, pulling the charged solar particles westward, where they hit the neutral particles along the way, all the way into the inner magnetosphere, causing Steve to show up at lower latitudes than normal auroras. So this ion drift has been investigated via satellite for almost 40 years now, but Steve is the first visible indication of it. And now I think the really cool part of all of this is that the phenomenon has officially been named Steve, all capital letters, and stands for Strong Thermal Emission Velocity Enhancements.
We're so boring.
Yeah. So they did this to match the original name given by the awesome citizen scientists who captured this beautiful site. Yeah.
Okay, and finally, Astronomy Not in the News. This is a segment that we do where we highlight a story that has generated a lot of discussion within the field of astronomy but hasn't made it into the mainstream news. This month is an article published by Coral Wheeler. She's an astronomer at Caltech. However, the story itself is largely a rebuttal of articles by Stacy McGaw and Federico Lelli of Case Western Reserve. McGaw and Lelli, in their previous work, derived a relation between the speed and the speed at which stars are orbiting the centers of galaxies and the total amount of material in the galaxy, which is related to the brightness. So this is essentially, brighter a galaxy is, the faster things are moving around it. So this is a whole bunch of different galaxies, and there's this relation. They essentially derived a slightly different relation, but related to this. They suggested that the relation does not require dark matter in galaxies. Instead, they suggested that the effects of dark matter on large scales must be the result of an incorrect understanding of gravity. For those who keep track, this is something like MOND, modified Newtonian gravity, alternative theories of gravity. However, in Coral Wheeler's paper, she and her co-authors used models of galaxies that included several different forms of dark matter and required those models to fit an already known relationship between the speed and brightness of stars in a galaxy. And they showed that the relation that McGaw and Lelli claim to see exists, the relation that McGillian Lely claimed to see exists because of the existing known law, or existing known relation, and because of, but not despite, dark matter. This is an example of one of these debates that are often occurring in the background in astronomy and many other sciences, and behind the scenes for most of the public. The vast majority of astronomers and astrophysicists agree that dark matter, I'm sure Dr. Killick, wherever he is, would agree, that dark matter is a real thing. And modifications to Einstein's gravity do not do very well in explaining all the available evidence about dark matter. This is very similar to the current debate that's going on over climate change, and that there persists a very small percentage of astronomers who are yet unconvinced regarding the existence of dark matter, but might be using poor methods or science to support their claims. All right, that is all we have. Thank you all for coming.
Thank you.
Enjoy the rest of the show.